Special relativity is the relationship between space and time at speeds near the speed of light. Let's think about the effect of special relativity on time. Consider a train passing by a station. If we have one observer in the train and one standing by on the platform, the person in the train operates a light source with mirrors on the ceiling of the train car at a height d. Reference frame of the person on the train. It takes light to travel up and down between the mirrors once, 2d over c, the speed of light. The observer on the platform doesn't see the same thing as the person on the train. The observer on the platform sees a little bit of movement in the light in the x-axis. To the observer on the platform, the light travels a distance according to Pythagoras' theorem. L equals the square root of d squared plus v t prime over 2 squared. The height of the train d remains the same the entire time since the length is only contracted horizontally, not vertically. We can use this fact to relate the time of travel for the light on the platform to the time on the train. We can call 1 over the square root of 1 minus v squared over c squared equals gamma, the Lorentz correction factor, so that t prime equals gamma t. If we replace v over c with beta, we notice that beta is never greater than 1, since the velocity will never be greater than the speed of light. Let's take a look at something that comes from this result, the twin paradox. Suppose twin A remains on Earth and twin B flies off in a rocket at 80% the speed of light over a distance of 4 light years. In twin A's reference frame on Earth, the time that has passed in the second twin's journey is 10 years using the time equation developed earlier. But what about in twin B's reference frame? In twin B, the rocket twin, recall our formula for the moving reference frame. In his reference frame, the Earth is moving away from his rocket and we consider his time to be t. Using the formula we discussed earlier, we can plug in our values for v, t prime, and c to find that he only experienced a travel time of 6 years. That's one quick rocket. Now let's move into another section of special relativity, length contraction. If we have the same moving train as before, with one observer on the platform and one observer in the train with a light source moving horizontally this time instead of vertically. In the reference frame of the observer on the platform, we see that the source moves a small distance horizontally. The time light takes from the source's initial position to when it is detected on its way back is L prime over speed of light minus velocity. It's different because the position of the source changed. We add together the time it takes for the light to travel to the mirror and back for a total time. Recall our formula for using the Lorentz correction. We just solved t prime when we know that the time it takes for the stationary position or the observer in the train is just twice the distance over the speed of light, c. We can find the total time by simply adding the two formulas for the light traveling away and back to the source. Using the relationship found earlier for time dilation, we can use the time in the initial frame to the relative frame to find a relationship between the length in the inertial frame and the relativistic one. Now consider our twins again in the same situation as before. The observer on Earth knows the planet is 4 light years away, so a round trip is 8 light years or 10 years in time, as we saw before. The observer on Earth can use our formula for length contraction for his twin on the spaceship, calculating the distance to be 4.8 light years, or 6 years in time as it was calculated before. But his twin on the spaceship still travels 8 light years in his own reference frame. So why should we care about special relativity? Well, GPS satellites rely on calculations from time dilation and length contraction to maintain accuracy. Without it, they would fail in minutes. Thanks for watching.